Good afternoon, everybody. That's pretty loud. Is it too loud or is it good? Awesome. My name is Miles Ward. I'm a solutions architect with Amazon Web Services. Big fan of MongoDB. If you are not interested in MongoDB, this is the wrong room and you should bail, because we're going to talk about that for about the next hour. There's plenty of chairs, so if you want to say on the internet that I've heard of that this talk is going great, or that it's going terrible, just put that out there and we'll see if we can fill in the rest of the chairs, because I think this is going to be a valuable set of information. I'd also like to introduce Chris.
Christopher-Biow, MongoDB, principal technologist and technical director. Been working in databases for about 10 years, and Petabyte's just get me jazzed.
Petabytes sound good to me too. So without further ado, we want to run one little quick chunk of code.
So we'll kick it off and describe a little later exactly what we're doing here. Those of you who know the terminology will also already be able to guess.
So let's talk about first MongoDB on AWS, best practices for that, so that maybe when you go home, you can build something that's going to run quite as big as this. I'll talk through the current, newest, updated guidance about how to run Mongo at scale, how to deliver high performance to your customers, and how to do that on AWS. So we've done a lot to try and simplify this process. We've published a white paper that describes all of this in long-form English. If you really like papers and maybe have long international flights, this is the way to go. The white paper has been summarized into a series of marketplace listings. So how many folks familiar with the AWS marketplace? Awesome. So in the marketplace, without any kind of setup work, without any configuration changes, you can launch a MongoDB EC2 instance at 1,000 IOPS of performance, 2,000 IOPS, or 4,000 IOPS on a single node. So that gets you a pre-built, pre-described 10-gen now MongoDB incorporated, blessed system that is ready to run production workloads, except for that whole part where I said single node. How many folks in here love running MongoDB on just one computer? There should be no hands. No hands from you. No, that's the wrong answer. Don't do that. Don't do that. The correct way to run MongoDB, as you know, is in a clustered mode, is in a sharded replica set node. So how would you do that? How would you build up a system that allows you to take advantage not only of the networking power and the performance of EC2, but also the provisioned IOPS volumes that are so critical to consistent performance from MongoDB? So we've released a series of CloudFormation templates. How many folks are using CloudFormation today? There should be way more people using CloudFormation than Marketplace. I'm just throwing it out there as a personal value judgment. So CloudFormation gives you a way to launch an atomic command, one message that builds a cluster, distributes EC2 instances, configures their storage, and in this template actually has a pair of templates, one that creates the storage and another that joins them together. So CloudFormation lets you take the configuration decisions that you've made and reduce them to code so they can go in your source control. Your infrastructure should, in fact, really be artifacts in source control rather than wires and cables and stuff plugged in. So we've also seen lots of different implementations for MongoDB on AWS. We have several different block storage systems. All of them expose different kinds of performance. I just got done about an hour and a half ago doing a detailed talk on EBS storage performance. Ooh, looky, we're building instances.
Fulfillment.
All right, so EBS provisioned IOPS provides the most consistent storage performance for structured data storage workloads. EBS provisioned IOPS is designed to provide within 10% of what you provision 99.9% of the time, which is a lot of the time. In comparison to standard EBS, that's like a rock. So provisioned IOPS EBS volumes also allow you to build clusters beyond just the IOPS performance of standard EBS. They allow you to go to 4,000 IOPS per disk. And since you can have multiple EBS volumes per host, we have tests showing EBS performance per node in excess of 90,000 IOPS. Does anybody want their Mongo database to go slower? Oh, stop it, you don't. So since that's available, we do, and we have seen quite a few customers building large-scale systems around the combination of MongoDB and provisioned IOPS. We also see a lot of customers very successful deploying MongoDB on the Hi1-4x large instances with local SSD. The SSD instances work great in combination as a part of a replica set system. So I'll show an example of what that looks like shortly. Standard EBS, again, is going to provide on the order of a couple of hundred Mongo ops with pretty high, relatively high variability given the design of that system around larger block operations. Provisioned IOPS volumes targeted at smaller block operations at lower latency will deliver significantly higher density. That's not a typo. Going from 200 to 4,000 by changing one configuration setting is a pretty important shift in the overall performance of a MongoDB infrastructure. And since you can use our cluster compute, that's CC1, CC2, CG1, CR1 8XL, Hi1 4XL, HS1 8XL instances, those instances offer up to 800 megabytes, not bits, megabytes a second of throughput to network to storage. And as a result, you can get in excess of 80,000 IOPS, even 90,000 IOPS. We printed 80,000 back when I hadn't done a couple more tests. So that's higher. Particularly, it's higher on the right side than the SSD-based instances from AWS. So at 80,000 write transactions per second in MongoDB, you're able to do at a density on instances that's very different than some other designs. So to compare the SSD devices to the storage service of EC2 and EBS together using EBS optimized as a flag, standard EBS provides lots and lots and lots of variability in comparison to the relatively, ooh, we're building even more instances.
We are fulfilled.
Ooh, much fulfilling. So the provisioned IOPS is in the center column at less than really 0.1% variability. And the SSD instances on the right-hand side, while very, very fast, very high density, if you're going to build a high-scale system, that's a useful tool to use. But they also show in the order of 5 and 10% variability on writes to disk. So if the transactions you do in MongoDB, if each individual event is something that an end customer experiences, it can make a lot of sense to have each one of those writes happen at a uniform latency so that you have a uniform good experience for customers. Provision IOPS helps with that. As well as you're building EC2 systems for MongoDB, certainly recommend the use of either ext4 or XFS, turning off the file system flags that don't add value for NoSQL data systems like no dir time and no a time, raising the file descriptor limits so that there's enough access to memory and storage utilities. You also want to set the disk read ahead low enough, down typically to 16K in order to eliminate overconsumption of provisioned IOPS throttled storage. You also don't want to have large virtual memory pages. That's a problem, and it's not a typo, and the italics are not for joking. You do need to snapshot volumes. I promise it's a great idea. Backups are awesome. So that process also, interestingly, increases the durability of EBS. The more often you snapshot, the less often you'll need the snapshots. How weird is that? So for the maximum scale production workloads that we're seeing that are sort of standard topologies, let's call it, you're typically seeing SSD instances used as 2 out of the 3 of a replica set. So this can be multiplied by way of sharding to dozens and dozens and dozens of machines. We have customers that are operating today on AWS at petascale, which is pretty outstanding if you think about that. The component of provisioned IOPS in this pattern is there so that when you run a cluster of this size, you still have the ability to snapshot to S3. Having your data at 11 nines of durability is good news. You should like it. So snapshots also now allow cross-regional migration. So you can take the data that you have in US East and ship it over to Singapore just because it seems like a fun idea. So on top of, again, this replicated pattern, you would shard for additional read or write performance for scale. So another option, another area, most of the work and optimization around most Mongo workloads focuses on the storage component because most users tend to run in a, let's call it a lean design, where you've rapidly overloaded the memory available on the instance. That's because memory is pretty expensive in comparison to storage. In contrast to that, the CR1 instance at 244 gigs of RAM lets you build clusters where you can easily get to terabytes of data in memory, which offers a totally different performance characteristic in comparison to interaction with any kind of storage, no matter how snappy that storage is. So strongly recommend, if you're looking at workloads where, again, every transaction is interacting with an end user, Mongo is strongly designed around the context of memory resident data, and the CR1 instances are offering a kind of performance that's totally unreasonable in comparison to other ways of doing the job. So with that, I'd like to introduce Chris. Chris is helping us build some pretty interesting systems on EC2 and MongoDB.
Miles, thank you. So this came up about 6 months ago, shortly after I joined MongoDB, wanting to bring things up to a higher level of scalability. And the idea, which I believe you termed RED, was to initially take a fairly inexpensive approach using the spot market. I'll go into some detail on what the spot market is, but using the smallest real instances where you have reliable access to some cores, the M1 smalls, doing that over, I don't know, how are you going to divide up a petabyte? Why not 1,000 shards? Why not a terabyte of each on each shard? That would equal a petabyte. A reader to test the query capability based on PowerBench, and this shows some aggregation queries, what we could do. One of the sweet spots for MongoDB is the ability to use secondary indexes to provide fast, typically second or so response to the end user, to the application, where, and this is key, Miles was talking about, you're looking with MongoDB generally for your working set to fit in RAM. This doesn't mean the entire database fits in RAM. Obviously, we don't have a terabyte of RAM per M1 small. We have 1.7 gigabytes. So we choose something where that aperture, about 1.7 gigabytes, would describe what needs to be in memory, and then, as many as the PIOPS will deliver, well, we'll get to that in a minute, as many as the local disk will deliver in this case, within about a second for anything that's not already available out of indexes. Developed that a little bit, and Miles went to some of his people who wanted to show what PIOPS could do, since my idea was primarily based on doing things inexpensively, quantify that in a minute. And Miles said, well, if we give you some PIOPS, what if you use larger machines, probably not quite so many of them. We finally wound up with a formula of 44 instances of the CC2 8X large, 60 gigabytes of RAM, and very importantly, as we're trying to load quickly, 10 gigabits per second interconnectivity if you put them in a single group. On each of these instances then, there would be 24 1 terabyte mounts, 1,000 PIOPS per. And in this case, we were using YCSB, the Yahoo Cloud Serving Benchmark, as our data source. Difference between the two I'll get to later. PowerBench scales out better. I wouldn't want to try to use YCSB across 1,000 nodes. And again, some sort of an aggregation query payload. This has to be, this talk I'm giving had to go through an editor here. One of their primary functions is to be trademark police. So if I simplify or change any of the key Amazon product terms, I want to credit it. So PIOPS are short for provisioned IOPS. EC2, short for Amazon's Elastic Compute Cloud. And spot instances, we'll get to sentiment and spot instances later, but we'll just call them spots. Auto-scaling groups are going to be one of the key capabilities. In fact, it's what I was just showing you there. If you watched as it went by quickly, we'll go over it more slowly. Those are a good way, not only of, as it would apply, automatically scaling the size of a group, but also just instantiating a group and push to the cloud the management of that group. So I'm going to back up a little bit and talk about why Miles and I are up here on stage together. There's quite a complementarity or synergy between MongoDB and AWS. MongoDB itself, for those who may not be familiar with it, is a document model database within the overall NoSQL database movement. Key for us is developer adoption. Our core strategy has, since the inception of the company, been adoption over trying to, for example, go after revenue and doing that through developers. We're complementary to AWS because one of the things we don't want as, at least traditionally, a fairly lean startup, and we're still going to run lean after getting a large funding round, is we actually own next to no hardware. Almost everything that we do internally is hosted on AWS. Like other NoSQL databases, we take an approach of scaling up with commodity hardware as far as the power, performance, price point makes sense, and then scaling out using multiple shards to keep that at a reasonable price point. Additionally, what I'll call scale around is the ability to use replication, not shown here because we were simply going for that scale out. There's absolutely no replication, no high availability in what I'm standing up here because the purpose of this was to sort of stress those limits. Go back one second. There's a lot of hype about many of these new technologies that have changed our world the last 5 years, NoSQL and Hadoop both. What's interesting is that although you'll see the balance of the hype, particularly from the analysts on the Hadoop side, the developer activity shows something that's much more evenly balanced. Just Google terms, you see MongoDB trailing by all of a few months the increase curve of Hadoop. And if you look at what developers are actually doing, and maybe we have an unfair advantage here that we have a developer-first strategy, developers appear to be spending more of their time producing more of their applications, and I don't have a way to prove this, but I think driving more business value than they're actually doing with Hadoop. So we won't compete on the hype. We definitely will compete for your time. PIOPS are key, I think, for almost any database that you would want to run on the cloud. As a general rule, the database world is rather queasy about shared storage. It usually doesn't work out well. It's usually over-provisioned. And the economic model behind it usually creates a tragedy of the commons where, well, actually, recent major news story has as one of its elements a badly over-provisioned back-end storage system. PIOPS get you away from any concern with that. And a lot of applications don't need them. If you're running a mail server with the occasional spiky load, that commons with the storage a little bit oversubscribed works well. You don't want to pay for PIOPS, and if you don't want to, don't, because PIOPS are expensive. But when you're running a high-performance database, you're typically going to be limited by I/O. You're certainly going to be on write, and depending upon read, if you're doing scattered reads, almost all databases are going to line up the same way there. You're going to be limited by your I/O. So I'm not sure which was chicken and egg between AWS and ourselves on PIOPS, but the two were basically built for each other. To this day, about 40% of all MongoDB customer usage is on AWS. Internally, I said we have next to no hardware. About 90% of our usage is on AWS. And if you were to scan the ports within AWS, maybe by accident, you'd actually find that there are more MongoDB ports open than Oracle ports. It's that prevalent. The two really fit together. It's peanut butter and chocolate. Differentiators. Why does this make so much sense? How has the adoption followed so far? Both of them provide fast time to solution. You've got the ability with a document database model that scales well, scales up as much as you to the cost level that makes sense there, scales out well. You can get to your solutions fast. I would urge everybody not too fast. One of the hazards of a developer-driven adoption model is standard anecdote. Developer's been stuck for 6 months trying to solve a problem on a relational database, reads something on Stack Overflow, tries MongoDB. Half an hour later, maybe past that problem. What scares me is going to production the next day. It's still a database, still requires some discipline, and that's often where we come in. So with that caveat, don't go too fast. With the two, you can get to your solution very fast. You're not waiting for hardware. You're not waiting for software. And you've got a type of database that solves some problems that have traditionally been very difficult. You can easily distribute your data globally on both sides with the replication within MongoDB and using the various regions, careful not to say zones, the various regions of AWS. The two of those fit together very nicely with respect to I/O patterns, et cetera. The document model allows the freedom to get away from problems that have traditionally been difficult using the relational model, the tables and columns. If you find yourself doing violence to your data to squeeze them into table and columns, you're probably using the wrong type of database. Certainly there are application domains where relational databases make sense, but when you're spending most of your time messing with your schema, afraid to make changes because they'll destroy the schema and cause you to re-engineer, that's where the document model database fits. MongoDB, in addition to our core strategy, our differentiators technically are the use of secondary indexes to provide sub-second response to the end user. And this extends to geospatial indexes, text indexes, and a very granular type of security that the US Department of Defense and Intelligence community has pushed us toward, where within a document you want to be able to determine who can see what when and have levers to turn that on and off. Finally, in the package is the ability to do analytics. There's a dividing line here. There are analytics you're going to run with Hadoop. If they're not going to benefit from indexes, if you're going to be scanning your full data anyway, if they're going to run overnight anyway, that's probably the realm of Hadoop. But we're going to put as much as we can, and progressively with our roadmap over future versions, into that sub-second realm deliverable to the end user, the online, the operational database versus the offline analytic. So, where this whole conversation started with Miles and myself, it would be cool if we could really test the scale out of MongoDB. We tend to drive ourselves what we do internally based on what our customers do. And we have customers in this realm. The problem is they generally don't talk to us, won't tell us what they're doing until they have a problem, and then they still sometimes won't tell us what they're doing. So I wanted to have a tool where we could quickly say, OK, we'll stand up a petabyte database. Customer case would have to justify it, but that happens. Wanted to learn to do that specifically on AWS, given that it can be done economically. I'll quantify that in a minute. And also wanted to build this on some customer data. We're still working on that. This is a project in progress. And you'll see updates. I'll tweet them as they come along as we apply this to something other than the synthetic documents of Yahoo Cloud Serving benchmark. And then finally, wanted to get past that petabyte barrier. So the inexpensive approach is to use these spot instances. This is a quick look across all of US East 1, all of the zones in that region, at the spot market over a period of several days. You'll notice our US East 1B won't be your 1B. You may have a 1A, we don't. This varies by account. The actual zones are randomized over accounts. But for the three that our account has access to, well, pretty quick look at this. Doesn't look like we want to compete in 1B. The scale here is a little hard to see, but you're looking at people who are bidding, don't ask me why, $5 per hour for these spot instances. The baseline down there at the bottom is 7 mils, 7/10 of a cent per hour. And in fact, outside of 1B, during this particular week, you were going to pretty much be paying 7 mils per hour per spot instance, assuming you had the sanity to stay out of East 1B. Now, this is the way it looked a few months ago. Coming up on AWS, yeah, the market heats up a bit. So we picked the 1D market and drill in on that a little bit. Now, the scale is not so expanded here. That little blip you see at 2 cents versus 7/10 of a cent, don't confuse that with the order of magnitude we had in the previous graph. So yeah, if we're in 1D and we don't really mind occasionally losing our instances, and if one of these runs doesn't work right, other than the one that I just did in front of you, which I didn't want to lose, yeah, I just run it again. So we're actually going to be able to rent instances at 7 mils per hour. That's a kiloshard for $7 an hour. That's the proposal. So wanted to see how cheaply I could do this, and got it notionally under $200. We're going to need a few extras. Some of these instances will be stillborn. Some of them may respond slowly over networking. And if you look at the run I just did, actually, I don't know if we rejected any. Some of the runs, I just reject some because they're responding a little too slowly, not sure why. So we'll start actually 1,050 to get a full 1024 kiloshard. The configuration servers, which I'll explain in a moment, I'm going to use 3 of those. And I don't want them to be bottlenecks since they're metadata for the entire cluster. I'll run them on M1 larges, keep them up for a couple of days while I'm messing around. We'll put our terabyte out as a snapshot on S3, and then make 1,024 copies of it on EBS. This, after all, is a test database, and as yet, we're not running this on real customer data, and one YCSB document is about as pretty as the next. So this is reasonable for the purpose that we're trying to do here. Now, are we really moving a full petabyte around? Actually not. This is optimized out by the way AWS lazily provisions the elastic block storage from the S3 snapshot. It looks to us like a somewhat slower read anytime we pull a block off of disk that hasn't already made it over to the EBS side. But within an hour run for the types of queries that we're doing, it actually looks to MongoDB, to all those shards, as if they have that full petabyte, even though they'll never entirely pull it across during that hour before they shut down, and does a good job of simulation with the occasional slow I/O. Cost to move it to EBS actually is 0, as long as you do it within the same region. So started off on this trying to realize the cool, learning about the M1 small market. Mostly stayed in the zone I just showed you, our zone D of US East 1. And basically I've got many hours now of running kiloshard instances at $7 an hour. That fits nicely on the budget. Particularly when I'm dealing with unknowns, I like to hack about in Perl because it's got clumsy, somewhat aged language in some respects, but also has the Swiss Army knife for absolutely everything, particularly if you have to go parse random stuff you weren't expecting. Started out with the net Amazon EC2 package, learned better. I'll go into that in a minute. And then where that package didn't cover some of the things I wanted to do, just went to the EC2 command line and parsed the responses. Did not initially start with anything on the level of Chef or Puppet or CloudFormation because I knew I was going into an attempt to just scale out, sacrifice high availability or reliability for that horizontal scale. Chose YCSB because it's actually a terrible benchmark for a document database. It's a bunch of random noise fields and a primary ID really meant for key value databases. But it's sort of the only game in town. Nobody's standardized on anything else. And at a certain level, for the purposes I had, bytes is bytes. Modified YCSB just a little bit to add some numeric fields so we could do aggregations on those. Userdata.sh is a script that you can hand to the instance that you launch on AWS, at least with the Amazon Linux and Ubuntu, I believe. Very handy, and something I learned as I did this, push as much of the processing you can to this mega cluster you're building. Let those instances do the work for you as much as possible, and then check in. Looked across the options, T1 Micro, some previous work I had done, Micro-instances are great. Matter of fact, there is a little old server called smtp.biow.org that handles my personal email and my wife's gardening business website just fine on micro. But when you're doing something that is I/O and CPU intensive, micro-instances, not so good. You notionally have a couple of cores, you use them for a few seconds, and they go away for a while. So the M1 smalls were really the sweet spot for this purpose. Talk about how MongoDB itself is put together. I'm not going to go into a lot of detail, but just try to explain what I was showing. When you have a MongoDB sharded cluster, there are, in a production environment, 3 configuration servers. The one thing that MongoDB does in a 2-phase commit, fully transactional cross-document basis is manage its database. That's done among the 3 configuration servers. The second type of server is called Mongo S, S for sharding or routing. That points to the configuration database on the A, B, and C configuration servers, and also routes across the various shards. Replica sets are the dimension of MongoDB that allows you to go to high availability. I've already said that was not a goal here. Someday I'd like to do, actually, probably 2 or 3 petabytes with high availability. That's not something I'm doing right now, but it is a core dimension in a production MongoDB system. You're going to be using replica sets. Shards are the scale-out dimension. Each shard, and in some cases you'll have multiple shards per server. We did this on the high-end approach, the v.fast. Each of those is served by a single MongoD process. It's a daemon. The Mongo S's then learn which of the Mongo daemons, which of the shards have which data. I'll explore that a little bit later, and route the queries appropriately. For client load, running YCSB is about as simple as you see there, except for many lines of class path, just like any decent Java system today. So here's a pictorial of what a MongoDB sharded cluster looks like. Your 3 configuration servers there on the right. N number of routers up on top. Those are the Mongo S's. And N number of shards at the bottom. The default type of sharding approach used by MongoDB is to do it based upon range. This works very well for certain patterns. I'm not going to go into picking a shard key here. It's one of the most key decisions you make when you use MongoDB because it allows you to have your queries focus only on certain shards. Example would be a Twitter-like system. We have a number of large companies building their internal Twitter-like systems on us. You have lots of choices there about how you do fan-out on read, fan-out on write. We actually have a benchmark in work to help our customers make those decisions. This is where you would use range-based sharding and make it something intelligent so I can say, oh, this is user X. User X, everything that I'm going to need to respond to their query is over here on this shard. The other approach, and the one that I used largely for simplicity, is hash-based sharding. Hash-based sharding forfeits the option of concentrating a given query only on one or a few shards. In fact, it just about guarantees that any query will be flooded to all the shards. But for the purposes that I'm using here, this is adequate. And the great thing about it is it also floods all your writes so that we can get to that petabyte in a reasonable amount of time. It ensures essentially fair random distribution. So here we're taking a primary ID, in MongoDB, that's always underbar ID, and we are hashing it and then distributing it among a certain number of chunks. I'll show you what a chunk table looks like later based on what I just ran. So the process of building this whole system up using the spot instances looks like this. You start out with a spot instance request, and based upon the price you bid against that market, you may get any of these results. It may out and out get rejected, go home, bid more. Not going to happen this weekend. It will spend a certain amount of time awaiting evaluation prior to being rejected or not. There's then, after being accepted, some time awaiting fulfillment. The fulfillment may be partial, and there are discrete launch intervals. Again, not going to go into a lot of complexity about how the spot market is handled. You'll find both official pronouncements by Amazon and a lot of reverse engineering trying to understand what happens. But at the level we're talking here, it tends to come in bursts, and you'll see that on the run I just did as we look through it. And then finally, fulfillment. Now we have our instances. After that, we go through a series. Actually, the instances at the point which they're fulfilled haven't quite yet started up. They're just guaranteed to be provisioned. They go into a request queue. They go through an initializing stage. And then within my own cluster builder that you just saw, we select certain ones to be configuration servers. In this case, I pre-started my configuration servers so as to simplify things and add a little bit of reliability since I'm doing this live. We choose some Mongo S's. We watch them start. We find that they're running and answering up. As the Mongo Ds come up, they actually call into the configuration server via their local Mongo S's and say, make me a shard. I'm here. I'm available. And then finally, some of them, I'm not sure if I had any of this run, I will reject. If they time out, I'd rather they not be in my non-high availability negative redundancy cluster. So the flow goes something like this: spot instance request on the left. Again, I pre-started my configuration servers in this case, and then conditionally I start Mongo S's, the routers, and the Mongo Ds join in as shards. So where we've gotten, learned a lot, as I expected I would scaling out. Figured I would do this by orders of magnitude 4. At 4, probably about half of the coding was required up to that point, just functionally to make it work. Moved to 16, started to see some variations, and this is where a lot of exception handling and lessons learned that I'll get to later, ways to do things more easily so that you're not having to write Perl. I think I wrote a total of about 900 lines of Perl. About 500 of those are dead now because I found better ways to do things. Going to 64, everything just worked. OK, only 2 more orders of magnitude, and everything's going to be fine. I'm not going to have to write anymore. Well, OK, at 256, chunk distribution time, for my purposes, was significant. You only do this once ever when you stand up a cluster. You go through the initial chunk distribution. So the fact that it takes 20 or 30 minutes with a huge cluster is OK. For me, it's not. So I decided, OK, I'm not going high availability anyway. Single configuration server kind of helped there. And then at 1024, you are really at the whim of the market. You'll get a cluster 3/4 of the way there. Somebody outbids you. Lots of interesting behavior there. I also found wire saturation with YCSB, which is why I went to bench press, which I'll address. Definitely learned defensive coding. Expect error conditions that you didn't think of up front. Monitor everything so that you could do postmortems and figure out what went wrong. MongoDB management service is a particularly useful tool here. It's free, something that we offer on the cloud to anyone running MongoDB. It will allow you to see about 36 metrics per server. Some of the gross stuff like CPU, IO weight, et cetera. Some of the fine stuff like database lock percentages, et cetera. One of the things that we both learned, despite our tendencies to the contrary, is don't get sentimentally attached to these little spot instances, even if they have really cool instance names like Bad B. Keep refactoring, try things out, and be ready to throw away, as I said, most of your code. And then throw everything you can to the side of the instances so they do the work up front. And the chunk migration wound up, again, because I'm standing up 1,000 servers, I don't want to take 20 minutes to shard them out. That actually mattered to me, where it probably wouldn't if you were a data center standing up 1,000 for business use. The refactoring led me to move from YCSB to, at least for the kiloshard distributed cluster, bench press from Palomino Labs. It's a fairly early 0.1-ish level, but works very nicely, has its own little server using Zookeeper internally and quite a bit of Apache software to distribute the load, and then you have an individual load runner at each of the shards so that you aren't dragging all of that traffic across the network. The database, the documents are being generated locally. As I said, more and more of my Perl went away and moved to server side. Something like global shell, very helpful so that you can address any named subset of your cluster or the entire cluster and send commands and just have them take care of everything. For instance health, I've started moving away from polling to a very new 0.1-ish open source project called Surf, which provides, I think I was the first one to take anywhere near 1,000 shards, and it scaled out quite nicely, allowing each of the shards to share heartbeat with all the others, uses a gossip protocol, and it requires a little bit of tweaking as you scale out, but allows you from any shard to see how the rest of the cluster is doing. Also did a little bit of work with Union Bay Networks. They are a value-added service on top of AWS. And Miles, you want to take this one?
Sure, absolutely. So UBN is a part of a team uniquely named in Union Bay in Seattle. They've built a tool for wide area network construction and network optimization. So that also makes much easier to implement the security of that connectivity. So we built these systems inside of VPC to ensure that we had network ingress egress control, and UBN allowed us to connect one region to the other region with a lot less configuration steps without the VPN hardware devices from AWS and with a sort of a push button deployment. So pretty useful tool for us, and made all this get done fast. There are folks here from UBN, so and they're good looking.
There they are.
So if you come in after, I think they have a survey and a gift card if you're interested. So they were awesome. So thanks, guys.
So helpful in giving secure, manageable communications as we're working to apply this across the regions. Here's, wouldn't be complete without some charts showing load rate. I talked a little bit before about your working set fitting in RAM. Any database obviously is going to be happier when everything fits in RAM. So it was interesting to see that from a load perspective, there's a little bit of a dwell at 1x RAM. Basically, this is the point at which we can no longer mmap everything and flush it lazily to disk, and we need to actually ensure we do a transactional commit to disk. So you see a little bit of a dwell there and a slightly lesser slope once we hit 1x RAM. Now this is another case where I'm going to change by order of magnitude the scale, this time in the horizontal. So here we're looking at the first, about 2.5 hours to get to 1.2 billion. Here's the path, I'm sorry, that was, yeah, 1.2 billion. Here's the path over almost 12 hours. So you see a few of those dwells there where you've got some additional mmap flushing activity going on, but it was quite happy. You expect over time, as the proportion in RAM declines, for this slope to become a little bit less, and was quite happy with that actually, particularly as it scaled out across this number of shards. So now the deluxe proposal. Miles, you want to talk about your thinking there?
We've worked with a lot of customers, and we were excited about the 1,000-node implementation as a prototype, as a way to push the outer boundaries of the automation tools and the bench testing tools and the other pieces that are helping MongoDB customers experiment at these kinds of scales. But we also know that in production, with most end users, that operations at that wide and that small is a little weird. Most folks don't do that. And they don't do it for a couple of different reasons. So part of that has to do with the density of manageable resources. The other part of it is this example uses the spot market, but to do this in the normal market is easily 10 times as expensive, and that makes that kind of an implementation not cost efficient. Provision to IOPS also allows you to radically increase the storage performance of the individual instances. So if the local ephemeral disk on those M1 smalls can grind out about 100 IOPS, the provision IOPS storage, like we talked about before, can grind out 40 times as much per volume, and you have 24 times as many volumes on each instance. So it's much, much, much higher performance at a much smaller, more manageable cluster size, which also lets you do the mathematics around regional distribution as well as AZ distribution with easier building blocks.
So this one, much more applicable to actual production use. 1,000 shards with negative redundancy, probably not the way you would do anything for more than an hour. Some results here. We went with the CC2 8x large instances, 24 terabyte mounts. This particular one was 4,000 PIOPS provisioned for each of those. And again, you're looking at, let's see, what's this? About 2.5 hours to get to the first 3 million. Notice these are much larger documents. These are 64 kilobyte documents, whereas previously some of the trials I was running was with 1 kilobyte. A PIOP gives you 16 kilobytes. It's kind of a shame to waste it on a kilobyte. So it made a little more sense to pick somewhat beefier documents here. Again, you'll notice a rather brief lull right around 100% RAM. And I'm sorry, this is the one where I'm really going to take out the horizontal axis. This is the first 3 million over 2.5 hours. Here we go all the way to 100, just south of 100 million. Again, this is one server over about 5 hours.
One of those nice straight lines. I like those a lot. So we've also done a lot of looking at MongoDB's interaction with storage is different than a relational database. It does work to serialize I/O. As a result, can grow in I/O size and a document size larger than the individual sort of typical 4K operations that it does to the storage system. So this is write throughput in kilobytes per second against each of the individual disks. So it's not 1,200 K a second for the whole disk system. It's for each of 24 distinct disks that are attached to that tool. So as we got up to full load, you can see that's a pretty steady state over the course of the period of time there, so a couple, 15 minutes or so. So the Provision IOPS data storage system really allowed this tool to really increase the density of that deployment, maybe make the management a little bit more straightforward, and reduce the aggregate cost for operations over time.
And to be clear, the variation here is a question of load. The provisioned IOPS could have been absolutely flat if we were able to fully load them. Turns out moving a petabyte of even synthetic data around even at 10 gigabits per second, you hit network bottlenecks fairly easily, and a lot of the tuning and plumbing had to do with that. PIOPS performed flawlessly here. You'll notice this is one machine, 24 volumes attached, and I think CloudWatch lost patience with us after what's the first 10.
Typical.
So,
yeah, I mean, how many folks have done that thing where you shoot the dart at the dartboard, and if you get all of them right in exactly the same spot, they say, ooh, that's a nice tight grouping. This is a really tight grouping. It means that each of the volumes is performing at almost exactly the same rate. In many other systems, all sorts of other charts, if you do this with standard EBS, you do this on local ephemeral disk, you'd see a wide stripe, not a skinny stripe, because each of those lines, there are 10 lines consumed in that one row. So you're watching really direct performance against the demanded workload.
So more work to do. As I mentioned, I want to drive this in all of these dimensions across the petabyte boundary, do it with replication. I thank very much the PIOPS gods, whom I know not by name, but who granted this last week. I guess Amazon has a little extra inventory in, getting ready for the holiday season. So I was given access to it to just go to town. Spent most of the weekend doing it, and I don't want to spend every weekend entirely on PIOPS. There are other activities, but it was a lot of fun. So right now, as I say, everything's negatively redundant. It would be interesting to look at self-healing without going to a full replicated redundancy. Can I automate the cluster? So again, we keep a spare pool, and if a node goes down, its function just gets picked up by one of the spares. We definitely want to move away from YCSB. It has the benefit of familiarity, but it's just a wretched data set for a document database. So we're developing some benchmarks, particularly that Twitter-like application. Very interested in using customer data. Customers tend to be rather closed-mouthed about their petabytes. If anyone out here has petabyte scale data that they would be willing to share with me, I'd be very interested in incorporating it. That's something I think someday for a press release we'd like to say it was with customer X and here's the business case, rather than my rather admittedly synthetic approach. And then I would like all of my Perl script to go away so it's completely self-hosting using many of the tools that Miles talked about. So I'll close very quickly going back to the demo and explain what the heck we were just looking at. If my console cooperates.
5, right?
Yeah, I hit 6. Precision. So what we saw here was the launch of an auto-scaling group right here at the top. Launch configuration describes the individual units, the instance, what will become instances. The auto-scaling group describes how many of them and where they're going to be. It's purely an API out of the box with a few languages supporting it. I do recommend, if you're going to mess with auto-scaling groups, easy auto-scaling, very inexpensive value-added service on AWS has helped me a lot to see what I'm doing so I don't have to create a RESTful query to figure it out. Having registered the 2 of those, the auto-scaling group specified a certain size, in this case 80 servers, of which I wanted to harvest at least 64 to create a 64 shard instance. 64 shard cluster. You'll notice these are roughly 30-second intervals. I sleep until the next interval. It takes a few minutes for the first one to actually become fulfilled, not yet actually available. And it continue in an idle loop here until we get at least 64 of them fulfilled, sufficient to build the size cluster I want. We wound up actually with 71 of them enumerated here. These ticks then are individual reports in from these shards of borning saying that they've been instantiated, the I's, U, they're up, D, MongoD has been started, S, Mongo S has been started, at least the lowercase ones. And then you'll notice the numbers initializing. At first it's just a few. Sorry, no, actually the first pass, we've got 58 of them already started. These came up fairly quickly. The capital S there, initially starting only one Mongo S, which is required to get the cluster initiated. And then finally, the MongoDs, you'll notice all coming online. Finally, we've got the 64 that we wanted. The cluster at this point is definitionally up. And the last thing we have to do is that actual sharding, where all of these MongoDs that have volunteered to become shards in our database now are given their assignment of chunks of that hash space that they cover. So that's the ta-da moment. I guess we can take a look in this shard, this cluster. Let's see if it's still up. Oh, yes, it is. So this is a report on the sharding activity. These are the individual shard numbers. You'll notice that there are 64 of them. Each of those shards has 2 chunks, with the exception of the one at the top there that already started dividing its chunks. It got a little overeager for some reason because I haven't given it any data yet. And then these are the chunks within the shards, those offsets within the hash space that each is responsible for. That's a look into the one that I just created. Here's a look into the one built on the larger instances. Again, because we have, 8 shards per instance, we wind up with a total of 111 shards. And again, you've got 2 chunks per shard. So any final remarks?
Sure. First off, thank you very much for not buying thousands and thousands of M1 smalls while we were talking about this. If you had in the spot market, the demo would have crashed because the spot market price would have gone up. So that was awesome. Any other questions that you've got about this process, and maybe Mongo questions or AWS questions or the stuff we're working on? Go ahead.
What the hell would trusted advisors say about this?
Ah, no, that's spectacular.
Plant.
Yeah, we have a screenshot about this. So, so trusted advisor at this time, where is this thing? It shows that we have 677 EBS volumes running, and that only 3 of them are not slammed right now, which is great news. It means we're actually beating up disk. Trusted advisor doesn't like it from an instance count standpoint against compute utilization, right? So there are some monthly savings that could be had were you to, say, for example, buy an RI on said CC2s. Security has also got a couple of red dots because, we just sort of put it in a box. Any other questions?
The trusted advisor doesn't call me weird, only Miles does that.
It definitely calls me weird. Sure.
I missed the part that what happens when there's no processing available in your bid? You don't have anything available.
When there's no processing available in your, oh, like when
For
the
your
spot,
bid?
Yeah.
You don't get your instances.
Yeah.
I mean, what kind of app do you build where you can deal with having no instances?
So there's actually a couple of really great full walkthroughs of this. You've heard of Vimeo? You can watch video on Vimeo. Vimeo's pattern is 7 different bids at different price levels, right? And if at any of those different price levels across the different availability zones in the region where they want to operate don't work, then they're bidding in on demand. So you can pay the full rate for instances. The whole point of having access to Spot is opportunistically getting the cheap stuff, right? So you do have to be able to pattern back and forth between the two. And there are plenty of workloads where you're running integration testing against a MongoDB warehouse. You want to do that at once every day because you build software really, really quickly. So you run it on Spot. If 2 out of the ones that you do that week don't run, but instead you've changed the cost from $70 to $7, your boss might like it.
And internally, customer comes to us and says, yeah, we're looking at this number of shards. How's that going to perform? How's it going to stand up? This allows us to just go do it. Say, don't get sentimentally attached. You may get half your instances, and then you get outbid. But for testing purposes that I originally architected this, it's great. A 5 nines business on 1,000 non-highly availability negatively redundant shards, no.
It's bad. Another thing that we have seen folks do is imagine that you have a replica set established in reserved instance, high performance instances. You have 3 of those in 3 different AZs. You're following all the best practices. And you know you're going to do more reads in a given period of time. So you'd bid for new Spot instances, go from 3 to 5, and then be able to query against all of those. If they don't come up, your reads go a little slower. If they do come up, awesome. You can get a little more higher performance on read. Over here.
I have a question. What happens when you're for whatever reason, some of your shards in Mongo, this may be more generic Mongo question, has more activity than other ones?
It's a good one. That actually is a design goal of ours in large part. Yeah, you do want to spread the activity, but you want individual queries to the degree possible going to 1 or a few shards. And the trade-off for that is you get hotspots. If you're dealing with Justin Bieber's tweet and Justin Bieber winds up on a shard, that's going to be a hot shard. So maybe you spread his. But we will actually tend a little bit in design toward allowing hotspots so that we concentrate our load. That helps us when you have a great deal of concurrency because the concurrency will spread things. The other option, if you don't want that to happen, is what I actually did here, which is used hash sharding, and now there's no reason you should get a hotspot unless a single document causes a ridiculous load. The only way I know to do that is with unreasonably large arrays, which is why I would not recommend more than about a 10,000 element array in a document.
Any other questions? Thank you very much, everybody. I really appreciate you taking the time. Thank
you.
It is BDT307. The more feedback we get, the more we make this rock next year. So click the buttons for us, and we'll try to make it even more awesome. Have a good time at the rest of the day.